So,
Yes, we can hear you.
okay, excellent. Well, thank you for the invitation. So I'm going to talk about how we could define a set of practical FAIR principle for AI models. And this is the best and most important slide of my presentation. It is about combining ideas and expertise from multiple researchers. So let me tell you what we thought we could do as a team to define these practical FAIR principles. And so the first thing is, what is it that we want to accomplish? And well, I thank Ari for that great presentation because that set the stage for this. And so let's go to common ground. What is it that we know about FAIR? Well, researchers have been talking about FAIR for data, FAIR for software, and we recently studied this, how we can define FAIR principles in the context, for example, of high energy physics. But, you know, if you take a global vision of this, the reality is that independently of your domain of expertise, what we really want to accomplish with FAIR is to not compile a list of requirements, tedious or laborious. The end goal of this is to automate data management because we want to enable discovery and innovation. That's the bottom line. It is not a list of things that data sets should meet. So we described how to do this and selected this science driver if you want to go and take a look. But the point that you want to extract from this is that one of the goals for FAIR data is to enable data automation, data management, to automate that, to accelerate discovery. So in the same token, in the same spirit, how can we do this for FAIR models? And here the tricky part is that what is an AI model? Is it data that has been structured in a smart way through training and optimization? Is it software? Is it a combination of the two plus computing? Because you need to look at the outcome of an AI model, so you need computing. And so what this team considered that it was optimal to do was to first begin by linking FAIR data sets that are also AI ready. And that means that they can be used immediately to train models, to do inference, etc. Then we want to link these data sets to repositories like DL Hub. And then what we also want to do is to present the models as Ari described in a way that the models are ready to use to do science. And we also want to guide users as to when the models are producing sensible output. And here the goal is to enable reproducible, accelerated, and trustworthy autonomous discovery. You see, for data, we wanted to automate data management. Here we want to enable autonomous discovery. And so these are the goals. As in the case for FAIR data, we want to accelerate, sustain innovation and discovery. And the North Star here is autonomous discovery. And so what we have done in the paper that you saw in the first slides is to not only, for example, define rules to play chess, but we have designed the board and created the pieces. And so we selected high energy diffraction microscopy as the science driver for this. And this is the name of the game. If you can see my cursor here, we have the materials data facility. We publish the models there following FAIR principles. And then we use these data sets to create different types of models on different architectures, hardware architectures, vanilla GPUs. Then we turn this into an accelerated model for inference using NVIDIA Tensor RT. And we also use the Sambanova data system that we have at ALCF AI testbed. And then we go through the process of publishing the models. We provide all the information needed to, adhere to provenance metrics that people have been discussing, and we provide this to the user, the whole package, data, models, and the means to use the models. And so here's how it looks in practice. You publish the data, you have the model, you combine the two, and then use PhuncX, and then connect you to, for example, Theta G, if you have an account, obviously, in this computer. And then we use Globus to orchestrate the computing. And you end up with results that for the user look as if they were running the models from their laptops. So it eases the process. And here are some results. Here you see images that represent snapshots of X-ray spectroscopy. Here you're looking at peaks of a crystal structure, basically a gold sample that was studied at advanced photon source in argon. And what you can see here is that for the 3 different models that we created, a PyTorch model, the one in TensorRT, and the one trained in SambaNova, you obtain consistent results. So this means that it doesn't matter what is your level of skill or computing resources, you get similar results. And the same when you use the combo of MDF, DL Hub, Theta G. And so this is the key point, that for users, we have streamlined the entire process. Now you can go and run the models, reproduce results. If you want to get access to the model, you can do it, and then do with the model whatever you want. But this is the beauty of the process. Now we are helping researchers to combine scientific data infrastructure with advanced computing. And this is the vision for what we are actually doing. And Garden will be a central piece for this type of activities going forward. So that's it. And let me thank those that support this work with this slide. So if you have questions, please go ahead.
Questions? Folks on Zoom? Anybody? Okay. Okay, let me ask one question. Oh, Dan.
I guess so. Ellie, both Eliu for you and for the previous speaker for Hari. I guess it's a little bit unclear to me. Are all the resources for what you were describing and what in Garden being provided by Argonne, or is there a way that I could use DL Hub and actually run it on my own cluster, for example?
So that's a great question. So here you see 2 potential avenues. If you have an account, for example, in one of the machines at ALCF, then you can just go ahead and then contact our team, and then we can work around a solution for you. The other solution is, if you have a compute resource and you talk with Ryan, or you go ahead and deploy a PhunKex endpoints on your compute resource, then you can readily connect the models in DL Hub with your compute resource, and then enable the process that I just described. So there you have 2 alternatives. My thought here is that as we move forward in figuring out how Garden can go and meet the needs of a diverse set of end users, we'll come up with better solutions to meet the needs of different communities. But at this moment, those would be 2 different alternatives. You have accounts in leadership class supercomputing systems where you have PhunKex endpoints, or you go and talk to your local champion, and then you deploy PhunKex endpoints in computer clusters, maybe in NSF, supercomputers, etc. And then these pipelines can be brought together.
It seems like it would be nice if there was a way of kind of automatically doing this on AWS or somewhere else where you already had accounts. I don't know, without you having to necessarily deploy an endpoint for yourself. Maybe that's a multi-tenant issue. Sorry, not a question, sorry.
Yeah, I mean, the grand vision is to bring your own resources, but we're not there yet in an integrated way.
I think this will grow organically, Dan. I think when we gather enough insights from multiple users, we'll come up with a good solution that is good enough for a large cross-section.
So I'll do my 5-second question, which is, so you mentioned obviously the application-specific hardware, which clearly not everyone will have access to. But does your model, do you have like a different implementation of the model for CPU, GPU, RDU, or do you have does it somehow work on all of them?
No, that's a great question. So we have 3 separate models, and this is the point that we wanted to convey. It doesn't matter your level of expertise or your computing resources you have at your disposal. If you only have, inexpensive GPUs, this is going to work. If you're a person interested in computing at the edge and you want to use NVIDIA TensorRT, the model is there. If you're interested in training in an accelerated fashion using AI accelerators like SambaNova, there you have a way to do this. And at the end of the day, it should not matter how you train the model, the prediction should be consistent across the board because the model is interoperable and reusable. And the models that we published, for example, from SambaNova can be run on GPUs. It could also be run on CPUs, right? But again, this is, a set of initial steps. As we gather more insights from our communities, then we'll know what is the best approach here that is of use to end users.
Thank you. And on a scale of 1 to 10, how strong likely are you to recommend SambaNova to a friend? Just kidding.
There's an asterisk. Ben works for SambaNova.
Yeah.
He leaves. So say good things.
Full disclosure.
Okay. They are good. They are pretty good.
They're pretty good. I'll take it.
All right, thanks, Eliu.